In the following video, I'm going to talk about earth fault loop impedance, otherwise known as the ZS value. There's two values that we commonly look at, one being the 80% value and the other being the 100% value. For this video, it'd be very handy if you had the regs book in front of you, the BS 7671, and also the on-site guide. I'll go through some of the pages on them to help you follow through some of the circuits. In this video, we're going to look at earth fault loop impedance. We're going to be looking at the values that are in the regulation book, so BS 7671, and the on-site guide, again the current on-site guide edition. So if you've got both of the books in front of you, the first page that we'd want to be looking at is page 62, and that's in the regs, or page 131 on the on-site guide. So page 62 of the regs, and in particular we're looking at table 41.3. And in the on-site guide, appendix B, page 131, table B6. For these videos, they are the tables that we are concentrating on. So table 41.3 and table B6. So let's consider a 32 amp circuit breaker. So that's a BS 60898 circuit breaker, and in particular it's a B 32 amp. So as we look in the regs, table 41.3, you'll notice that this table is type B circuit breakers to BS 60898 or 61009, the RCBOs. So if we look under the first, this point here where it says type B, I've just marked it with the book, and so these are for all B type circuit breakers. If we wanted to look down at C, that's just below, or a D type is also below that, but we are just interested in concentrating on the B type circuit breakers. And in particular, we're going to be looking at a 32 amp. So we're going to be looking at the 32 amp here and the value that it's got there. So as you can see, that value reads 1.37. So if we're looking under the regs for a B type, it's given us a value of 1.37 ohms. So if we look at the same circuit breaker, so this time it's a 32 amp, just there, and it's a B type. This time, however, the value that we get here is now 1.1 ohms for the same type circuit breaker. Again, it's a 60898 or 61009, type B, 32 amp. So the on-site guide value is 1.1 ohms. Now the interesting thing is, for this one, is this value is what we call the 100% value, and this one is the 80% value. So again, just to go over that, earth fault loop impedance, page 62 of the regs, table 41.3, page 131 of the on-site guide, table B6, and we're going to be concentrating on a BS 6089 circuit breaker. It's a B type rated at 32 amps. The earth fault loop impedance, or what we call ZS, is 1.37 ohms in the regs, or 1.1 ohms in the on-site guide. And the regs is at 100%, and the on-site guide is at 80%. So moving on, we've said that the 100% value is 1.37 ohms and the 80% value is 1.1 ohms. Now one of the things that we need to be able to do is work out how to convert between the two. So if you just had the 1.37 ohms value, the 100% value, that's the 100% value. Well, we want to know what 80% is. So as a decimal, that's 0.8. So we simply times it by 0.8, and that will give us 1.1 ohms. That's really quite simple. It's a little bit more complicated. It's okay. So the 80% value, so we'll draw a line under that. The 80% value is 1.1 ohms. Now there's a couple of ways we can look at doing this. So we know that 1.1 is 80%, which as a fraction is 4/5 or 4/5. So we want to know what that missing fifth is. So we can simply do that by, we can go 1.1. So we can divide this by 4. And that will give me 0.275. And so this then is the missing fifth. So all we have to do then is go 1.1 plus 0.275, and that will equal 1.37 ohms. Now, going back to looking at this, we said we're missing the 1/5. We know that what 4/5 are, and we are missing the 1/5. So what we have done, we have divided what we have known, the 1.1, divide that by 4, and that has given us 0.275. So that has become the 1/5, shall we say. Let's put that in brackets just so it's... Now, when we have divided this 1.1 by divided by 4, this has also actually become a quarter of this, and as a so that's actually become a quarter, which as a fraction, sorry, as a decimal is 0.25. So all we actually need to do is 1.1 times 1.25, and that will also equal 1.37. I'm trying to do it without holding the camera and without moving the paper. 1.37 ohms. So I'll just go over that one more time. So we've worked out what the missing fifth is, which is actually 0.275, and so we've just added that to the 1.1, so that gives us our 100% value, which is 1.37. To find this, we've needed to find out what a quarter of 1.1 is. To divide, so we've divided that by 4, which is the 0.275. A quarter as a decimal is 0.25. So all we need to do is, what we know is the 80% value. So we go 1.1 times 1.25, and that will equal 1.37 ohms. So we're going to concentrate now on the 32 amp circuit breaker. We know that the 100% value is 1.37 ohms. Now we need to look at this equation here. Now this equation can be found on page 60 of the regs, and in particular it can be found on regulation 411.4.4, and that's ZS times IA is less than or equal to nominal voltage times C min. As you can see, ZS is the loop impedance, IA is the current that causes automatic disconnection, UO is the nominal voltage, and C min, this is the important thing, this is the minimum voltage factor to take into account of voltage variations depending on the time and place, changing of the transformer taps, etc. So we know that when we look at nominal voltage is 230 volts, but that's actually plus 10% or minus 6%. So that means that the voltage variations can go as much up to about over 250 volts down to around 216 volts or thereabouts. So what this C minimum factor is this C minimum factor, if you look here, it's actually recorded as being 0.95. So because we're trying to calculate ZS, or the earth fault impedance, we know it's 1.37, but we're going to actually calculate it now. So we know that the nominal voltage is 230 volts. We know that the C minimum factor is 0.95. So now we just need to find IA. Now, in order to find IA, we need to turn to another page in the book, which happens to be on page 370. And these are the time graph characteristics. So it's got here figure 3A4- type B circuit breaker, again 60898. So along here we have the different sizes of circuit breakers, ranging from 6 to 125 amps. Now you'll notice that with this table, it's what we call a logarithmic table. So along the base, it ranges, it measures the current, and you will notice that it ranges from 1, then it goes to 10, to 100, to 1,000, to 1,000, to 10,000. Now it does that in a logarithmic scale. So just looking here, each line represents, so 1, 2, 3, 4, 5 to 10, and then it goes 10, 20, 30, 40, 50 to 100, 100, 200, 300, 400 to 1,000, and so on. So that's along the x-axis, and then again along the vertical on the y-axis, it's now measuring time, and it goes from 0.01, 0.02, 0.03, and so on to 0.1, to 0.1, 2, 0.3, 0.4, 0.5, and so on, 1, 2, 3, 4, all the way up to 10,000 seconds. Now, when you are trying to read these, so we would want to concentrate on a 32 amp circuit breaker. As you look at this line here, so this curve here, which goes all the way from here, all the way down to here, that curve is the part of the circuit breaker that's where the bimetallic strip works for it's the thermal overload characteristics of the circuit breaker. So if you notice here that a 32 amp circuit breaker can roughly draw 40 odd amps quite comfortably, and it can do that for quite a long time. As the current increases, so basically as we follow the curve goes further and further, increasing the current, which therefore means if you go across to the time scale, it means that the more current that is going through that circuit breaker, the less time it will operate for. And this is where the bimetallic strip within inside the circuit breaker is heating up and eventually will break the circuit. Now, as we follow the circuit breaker all the way down to here, and then it goes into a straight line, at this point here, this is where it's an instantaneous disconnection. Now, it's quite difficult to read what number that actually reads. Now, if you are able to read it, it actually reads around it actually reads about this point here, and it's roughly about 160 amps. Now, you've got 100 amps here, you've got your 200 amps here, and so it's roughly around the 160 amp mark. Now, to make it a bit easier, we can look at this table, And so again, this table is just a reflection of the instantaneous disconnections, so basically these straight lines of each circuit breaker. So if we follow a 32 amp circuit breaker, we can see that the instantaneous disconnection is recorded at 160 amps. So let's now take that back to what we're doing here. So now the IA has now become 160 amps. Our 230 volts times our C minimum factor, divide that by 160, that gives us our 1.37 ohms. And that's quite simply how the 100% value is calculated. So in this case, a earth volt loop impedance of 1.37 ohms, that will tell me that 160 amps will flow, which therefore is just enough, which is the amount that we need to automatically disconnect the 32 amp circuit breaker. So we understand this equation here will give us a value of 1.37 ohms, which is our 100% value total earth volt loop impedance for the 32 amp circuit breaker. Now, something to understand is before the Amendment 3 of the 2015 of the 17th edition, where the C minimum value was introduced there, previously it was simply just 230 volts, divide that by 160 amps equals 1.44 ohms. So this value here was the previous value for a 32 amp circuit breaker. After 2015 of the 17th edition Amendment 3, they introduced the 0.95, which was simply to take it into account for maybe the lowest voltage that was allowable. So it's roughly around 218 volts there, very similar value to the -6% value of around 216 volts. So that's the difference between those there. So this is the new 100% value. This was the old 100% value. So it's important to understand the difference there. So we understand the 1.1 and we understand the 1.37, 80%, 100% values for a BS 32 amp circuit breaker. Now, my question is how close or what do we adhere to when we're on site? Well, the answer is this one here. This value here, 1.37, is what we might use when we are doing design calculations, but when we are actually working and we are doing measurements, we adhere to this 80% value of 1.1 ohms. We know that a 32 amp circuit breaker, a B-type, needs 160 amps of fault current to instantaneously disconnect it, and it needs to do that in a really quick time, as low as 0.4 seconds or 400 milliseconds. So it's really important that we adhere to this one. Now let's consider the 230 volts, okay, nominal voltage. Now this time we're going to ignore the C minimum factor, the 0.95 that we've spoke about previously. If we divide that by the 1.1 ohms, that will give us around 209 amps worth of fault current, okay. And if we were to work on 230 and divide that by 1.37 ohms, that gives us 167 amps of fault current. So you can argue that you can still go up to this 100% value and you'd still have enough disconnection or enough current to create an instantaneous disconnection because it's above the 160 amps. However, let's consider we're going to go down to that -6% value of nominal voltage, which is roughly around 216 volts. So if we were to go the 216 volts, divide that by the 1.1 ohms, then we'll still achieve approximately 196 amps of fault current. Even on the minimum allowed voltage, we'll still achieve the 196 amps, way above the 160. However, if we were to go to the minimum voltage and we're working towards the 100% value, so that's 216, divide that by 1.37 ohms, this time we're just shy of 160, about 158 amps. Now that would probably still achieve disconnection, but it's below the 160 amps that we know that the circuit breakers are designed to achieve instantaneous. So that's basically why we are always working to the 80% value, because we know that the minimum voltage of 216 will always achieve an instantaneous disconnection. And that's why we mustn't really go above the 80% value, the 1.1. Now, in reality, if you had a circuit that was a 32 amp circuit breaker for a cooker or a small shower or whatever it was, and you were reading slightly above the 1.1 ohms, you would still achieve the disconnection instantaneously, and that would still be okay. But we have to set a limit, and the limit has been set at 80%, and that's why we mustn't really ever go above the 1.1 ohms for a 32 amp circuit breaker. So the last part of the video, I'd like just to look at, again, table 41.3. We've been considering a type B circuit breaker, but let's now consider a type C and a type D. Now, we know that 1.37 was the value that we've been working to for a B type. Interestingly, 0.68 is the C type rating, and 0.34 is for our D type rating. So when you are considering using C types or D type circuit breakers, the earth fault loop impedances drop quite dramatically. Don't know how good you are at maths, but 0.68 is half of 1.37, and half of the 0.68 is 0.34. So that's the relationship, and again it works just using Ohm's law. That's the relationship between the B type, the C type and the D type. So it's not just simply as just changing a circuit breaker to from a B to a C, because you'd need to then consider the earth fault loop impedance. Now, if we go back to the drawing board, so we'll say a B type was 1.37 ohms, a C type was 0.68 ohms, and a D type was 0.34 ohms. So we know that 1.37 is 160 amps of fault current. Well, using Ohm's law, if we halve the resistance, Ohm's law, everything's proportional, so then we must double the current. So then that becomes 320 amps. What do you think happens to this one? We've halved the resistance again, so therefore we've doubled the current on this one. So a B-type circuit breaker needs 160 amps to instantaneously disconnect. A C-type is 320 amps. A D-type is 640 amps. That sounds like an awful lot for a 32 amp circuit breaker. So if we go back to the logarithmic tables, and in this case we've got a B-type here, and we know that a 32 amp, 160 amps. This time we're going to go to the next page where it talks about C-types, and again it says here 32 amps at 320 amps. And if we turn over to the next page, which then concentrate on the D-type circuit breakers, if we come here, the 32 amp, 0.4 seconds, let's just concentrate on that one, 0.4 seconds, 640 amps. So that's basically Ohm's law explained there. So I hope this video may help doing some of the calculations for your design or inspection and testing, but that's basically the relationship of the earth fault loop impedance. So basically, just to sum up the video, talking about the earth fault loop impedance, hopefully I've cleared up a few things, just explaining with the 80% and the 100% value, and how important it is that we adhere to the 80% value when we are actually on site working. We know that we've said using Ohm's law, everything is just simply Ohm's law, V equals I times R. Everything is calculated using that equation, and so it's really important that you understand that the lower the resistance of the circuit, the better it is, but the reaction to that is higher fault currents. Now, higher fault currents sound like a bad thing, but actually it's a really good thing, because it causes this circuit breaker to disconnect instantaneously, and that's what we want. And so please be, when you are working, consider the 80% value is the important value that we are to adhere to, but when we're doing more design work, the 100% value is where we might be at. Now remember, I have just worked with a 32 amp circuit breaker here, but the rules are the same throughout the circuit. The regs book, so the regs book and the on-site guide do go into detail on all of the other types of fuses, but it's really just it's the same rules that apply, but this time we're just working with the 32 amp B-type circuit breaker.